this final project, electric machine winding temperature estimation. So in today's video, I will go through a method that used to track all the experiments such that you will know which model performs the best. And then each time you run a model, explore, hyperparameter tuning, whatever, you will generate some results, and you want to actually log the model that being used in that run, and then you want to log the parameters used. You want to log the metrics, the performance of this run, and then you might want to log, few figures, plots from the, for example, matplotlib. So all that can be achieved by a tool called MLFlow tracking. However, this tool, while this tool is powerful, it is there is already a lot of video talking about how to run this tool on the local computer, but there is very few video on how to actually run this tool on the Google Colab, and log results, and being able to actually view display the results on your local PC or laptop. So that's what I will cover today. So essentially, when we work on the Google Colab, right, it is essentially a remote computer, and then it actually contains also another container inside that computer, and then it gives you a port exposed to you such that you can use it almost like a Jupyter notebook. That's how, the user, as you sit on your local PC here, you are like using the Jupyter notebook interface from the Google Colab. Because of that, right, if you run the MLFlow here, it gonna essentially, actually you not even be able to run it here. You might only be able to run it inside the container here. No matter what, there's a lot of trouble to actually, if this tracking gives you a URL, HTTP, whatever, that if you grab that and paste on your local PC, it won't work, because this only makes sense for like the local the cloud machine container. So one way to work around that is actually using a method called, I think a lot of guys are already present on this one, is the njrok. This package actually will expose this, and then push it to the whole internet, W3W. Like people from all over the world will, if it has that link, it will be able to view your results. That's something that I don't want. So I want a private sort of environment where I run all my experiment on my local, Google Colab, and then I can actually somehow visualize those results in real time on my local PC. In that way, I can leverage the GPU, right? The GPU here on the cloud, and then I can utilize the MLFlow, track my experiments, and see it here. That's exactly what we achieved. At the end of this video, essentially you will be able to actually track all your experiments like this, and then each experiment has an associated experiment ID, and then has a bunch of runs, and inside each run you will log the how that model performed, and then as well as essentially the model itself, You can even load the model back, make some prediction, and then what type of inputs you need to feed the model, each type of the data type of the inputs, and the output itself. In my case, I'm estimating the stator winding temperature, and then you could also log how it performs in terms of prediction, versus ground truth. Like you could log any image as well. So that's where I start this project and show you how to do it. So we mount our Google Drive. And usually I prefer to set up my workspace when I work on Google Drive. And then we start installing a bunch of packages that require, you can see MLFlow being installed as well. And then we can import the MLFlow. And you later on see this infer signature is also useful for capturing what kinds of inputs and output is needed to feed your model. And then I set up a bunch of other passes. So this nodrock, it is one of the approach that if you want to actually share the MLFlow, share your model or registered results, logged parameters to other people over the whole internet, then you might want to go this approach, but that's not what I do. The way that I introduced today is like you privately working by yourself, and then you train things on Google Drive, but you log experiment with the MLFlow, and then later on you can view it on your local PC. So here I just read in a bunch of data. And we can see that it contains machine voltage, currents, and other a couple of other time series data. And then we start doing feature engineering. I wouldn't go into details about all this ML stuff. It will be covered in separate videos. So after deriving useful features, right, we actually arrive at a data frame which contains some of the original data and some of the derived features, and then they will be used all together when we train machine learning models. And then right now, after feature engineering, we have 81 independent features and one single stator winding. It's our target value we want to predict. And then the utility function is just some of the function help me plotting the results. And then we start doing like a test train split. My testing profile is specifically two profiles, 65 and 72. And you will have a look about it here. Essentially, I'm trying to predict the stator winding temperature based on like all these other quantities. And then we start the portion where we have the model store. I structured the data structured notebook such that I can explore different type of models in my model store, and then log it through MLFlow. In today's case, I will show you the one with Keras LSTM wrapped with this Keras wrapper to make it compatible with the sklearn estimator interface, so that you can use it almost like a sklearn model. That's kind of common approach people use. Again, I will not cover that in details. For those people who are familiar with sklearn, they usually use this type of trick. It will be covered in a separate video. And now here we start constructing our model, our ML regressor inherit the Keras regressor, and then this is the key part where we build our deep learning model. Again, not the what I want to show today, but and here we give like that model a name. Sometimes it also common practice to kind of use the seed function generator to give that specific model a kind of a unique ID, but I didn't do that. And then this part is the MLFlow part. We can say that by default, my MLFlow is actually using my file system on the Google Colab. The reason is that if you look at PWD, right now my current directory is actually this content, whatever, go all the way up to deep PMSM. If you look at here in the file system, we could go to create enable system and then winding temperature prediction project, the project, and then deep PMSM. So you would notice that there is a MLRun folder here that is actually created by MLFlow, and then all the model essentially results will be logged here, and here is a bunch of experiments. So there is a default experiment, and then these are some other experiment. Each experiment, the MLFlow will generate a unique ID for it. And for example, this specific experiment, it contains a lot of runs. I already have a lot of runs here. And then each of these runs, right, it actually contains parameters and metrics like MSE or MAE, mean square error, mean average error, absolute error, and then the parameter used, hyperparameters or whatever, and then it also stores the unregistered model inside your artifacts, and then each experiment actually has a meta file. I will introduce this a little bit later, and each run here will have a meta file, which is important. So I will introduce that a little bit later. We will modify that such that we can visualize our result on the local machine. But right now, you would say that all the MLFlow result will be stored in the ML runs. Actually, later on, you will see there is also this ML artifacts. The difference between this one and that one is like, at least from my understanding, is the registered model will go to the ML artifacts. There are several experiments I already run the registered model, and then it is got stored at ML artifacts, and then that's why this folder has previously I have a linear regressor. If you look at here, sklearn linear regressor pipeline, that's the OLS I call it, and then it got logged actually here, registered, and then these are kind of four, kind of 1, 2, 3, 4, 5 typical files. Usually, the MLFlow will use to specify environments of the model, tool on the environments, it needs to reproduce the result, reproduce the model, and the model weights. The model and model weights are kind of located inside the model.pico file. And then there's some meta information stored in ML model. It'll be all easy for you to understand once we open MLFlow on local side. And then yeah, this is another model. So that's kind of what I would like to show right now. Also, you are free to actually log other files, other artifacts other than model. For example, I logged PNG, plots showing like an overlay between my prediction and my overlay between my prediction and my ground truth, things like that. And here, this is a parse library that parse the URL such that you know that this logging system is using the file. Sometimes there's other options that you can actually make it save on the HTTP. But we'll talk about that a little bit later. At least at the beginning, I would just use the file unless I want to register the model or whatever. But here I can define the experiment name, and I just define local experiments, indicating that the model is not registered yet. And then I set the experiment to that specific experiment, and then we can use ML get URL to kind of, again, this is not, but just say it's using file. And this is the command to just show you that you have options to say search how many experiment is there. Usually you just require like one experiment, and then inside that experiment you run a bunch of runs. Right now I'm using this one. The other ones are like the one that generated when I first started learning this tool. And then you go to the training session, right? And then you see that my data is like a pandas data frame. And most important thing is you wrap your code logging with this MLFlow start one. And when you write this way, when you go out of this ways block, actually it's automatically called MLFlow end run, so that you don't need to manually like take care of when to end a run. All I want to do is like I essentially fit my model, and then I make some sort of prediction, and then here I train the model, here I make the prediction right on the test data, and then I grab the signature such that my MLFlow can know what's the input of the model, what's the output of the model. And then here, if the tracking URL type store, this is like what I showed previously using the parse. Using this parse, it will tell if it's a file or HTTP, right? So if we are using file, it will call this one without registering the model. You could feel free to modify this code, but essentially, what I want is like initially, if I'm using the local file system, then it will be unregistered model. And then essentially we can sort of run this, and then it will train. So yesterday I had a little bit error when I play with some other stuff, but let's just try if it runs. Yeah, I kind of try to package everything in modular, such that I can treat almost like my deep learning model as if I'm training the linear regression model, so I can reuse this structure again and again. That's one of the reasons I try to avoid coding like this if the model is LSTM, I do something different. I try to incorporate the pre-processing or data reshape stuff into the definition of the model itself. That's kind of a general sort of thoughts on designing the code. But um, another thing I want to point out while it's training is so here there is a verbose. You could read the documentation on the wrapper itself. But there is a verbose that inherited the sklearn. When it is 0, it will not. When you call the model.fate, it will not output anything. When the verbose is actually 1, it will output like a progress bar showing you each epoch. It will just there will be just one progress bar, and the next epoch will override that. And when the verbose is set to 2, essentially you will see the similar behavior. What I am doing here. Essentially, for each epoch, it will output some debugging, progress information. And I feel the place that yeah, here is where I passed in the verbose 2 overrided the default 0. Right? So we call model fate. It will supposed to kind of just train it for 10 epoch. And the training itself will take a long time. Generally speaking, in DNN, if your loss, training loss kind of go down, it's a good sign that your model at least is not like diverging, but it's not meaning that you have achieved what you want. I will cover later why this LSTM is not performing as well as even the linear regression model. If you see this linear regression model we train is much better than this LSTM. I will cover in a separate video why is that. But again, we focus on kind of the MLFlow in this video, and we can see that we are training on a GPU, and this is like showing you how you can actually log the model back. We'll perform this part a little bit later. Log the model back and then print all the weights, things like that. But right now, actually, we have already run this, and if you see, I have a bunch of MLFlow log command. Here is log the actual model, and there's some other place where when I call this report plot, I essentially also wrote MLFlow, MLlog. If we have a look at here when print score is like called inside the I believe plot residual whatever actually print is called in print, and then inside the print score function we can see that I do have this MLFlow log metric which it logs the MSE a bunch of metrics from sklearn. That will help like judge if our model is good or not. And then I kind of also logged 2 pictures, right? I think the place that I logged the picture was like MLFlow log figure here. as well as the MLFlow log. When I plot actually here, plot compact. Log the first feature and main figure, and then the second figure. Yeah. So that's how I actually log the result. Essentially all these result presented here will be logged by the MLFlow. If you want, you can kind of write code to log the training loss, but in my opinion, it's not very important. And we can see that because we defined the experiment to be local experiment, actually it's this one, and then there's some new stuff showing up. So now I will show you how to actually open MLFlow. And if you directly spin MLFlow, like if you directly spin MLFlow, inside here, it won't work. I will just show you for an example. So we need to navigate to this folder first. To paste inside the Google Colab, you use control insert. Actually, forgot, maybe shift insert. Yeah, shift insert. And then we will move there. And after we move to this folder, that is parent of ML runs, we could spin MLFlow UI. So after we spin this MLFlow UI, right, we would get like this URL, this server URL. Usually you could just paste this, fucking copy here, which in the Google Colab is not Control C but Control Insert, and then you paste it here, Control V. So this won't work. The reason is obviously we are right now on the local PC, but this MLFlow actually was spinning at cloud or at inside the Google container. So I'll kill this. And one of the way that I make it work is that I installed the Google Drive on my local computer, such that you just go here and Google Drive, and then you can download it. And then after you download Google Drive, right, you would have the Google Drive actually here show up on your local PC, so you can see that I have a C drive, I have a Google Drive, and then on the Google Drive, my drive, I would essentially, the Google will start syncing between your Google Drive and your local laptop. And then we could see that I have this winding temperature prediction. If you want, you can right click and make it available offline. That will accelerate the minimize the delay between the two. Otherwise, you have to probably sometimes wait for it to get synced. But essentially, what I want to show you is that this has the same amount runs folder here. And we would you can open the VS Code and open it, and navigate to the same place. In my case, I would just navigate to the parent folder of ML runs, which is actually the deep PMSM. So here we would navigate to the projects and then city. We'll navigate to this folder and you see that ML run is actually here. So at this moment, I could just spin up, just show you like ML. Actually, sorry. MLFlow UI. I could potentially just spin it here, and I will get kind of the same thing. I will get a URL that my local server URL. And if I paste it here, this will show me the MLFlow UI. And if we look at the local experiment, is where we log our model. There was a model that got logged like 35 minutes ago, and it's because I paused the video. So, but this one is the model that we logged. And if you right now just open it, there's one problem. This thing will start refreshing and it will be refreshing forever. You can see the matrix is kind of logged correctly because if you sort of going back to Google Drive, the matrix here, MSE 66, MAE 6.4, 27, 0.9. So MSE 6.6, 6.4, 27, 0.9. So the matrix is logged correctly, and the thing is the artifacts or the model and the pictures are not showing up. One of the reasons for that is, you log things in Google Drive, so it puts the absolute address pointed to Google Drive. I will show you that. So each run has a unique run ID, this D2 whatever. So based on this, you could trace. It's my experiment 6.3 whatever, and then the run is D2 whatever. So when we going back here, right, we can go to the ML runs, and then this is the folder for local run, and we would need to find the specific run, which let me see is the D25. It's D25, this one here. So we can actually see there are a bunch of files being logged, including our LSTM model. However, it's not showing up. One of the reasons for that is if you look at the meta file, YAML file associated with that run, it is pointing to a location which use the content drive. This is obviously our Google Drive path. So one trick you can use is you can just kind of modify this, and then you know kind of where that file is, right? So you can go to here, and then you can go to this file, and you can go to artifacts, and then you could easily paste this on your browser. This will help you convert this, and then you can copy the whole thing. This will help you convert it into this file format. see what I mean. So it's file G, whatever. This is like the path on your local computer, right? So you can use that instead of first, and then you save, and then you should be able to go back and refresh. Here, once you give that pass on the local, your model will show up, and you can see that it logged what type of inputs are we using, some of the voltage, currents, machine speed, and a bunch of derived features, and then the output is like the stator winding temperature, and also nicely giving you all the data type. And then also by following this code, you could actually load the model back and do some inference. And also you are able to load it back and print the model weights, like I mentioned earlier. And we can see the performance, this plot is also kind of captured. So it's very, very powerful tool to help manage your experiments. As you can see that I already run a bunch of other experiments here, and I actually previously registered my linear regression models, and the registered model kind of looks a little bit different than the unregistered one. If we want, we can actually go here and register the model, but because I know that in my LSTM there are some bugs, so I have to fix that in next video, and then we can register the model. But the registered model itself is actually, you can see it open a new window here, and my linear regression model there, you can have like different versions, right? And they show you when it got registered, and then you can pick some of them, stage them, and then finally publish them, but whatever makes sense for you. So you go back to the registered model. The latest is version 4. And as I mentioned, the registered model actually is kind of located in a different folder. It's like inside the ML artifacts. That's why this OLS is there. But if we look at this one, right, this is like a register model. So one benefit of register model, or not necessarily register model, but one benefit of using actually HTTP, or not HTTP, not even HTTP, using this. If you look at this path artifact location, it does not use file system as well as the HTTP convention. It is using like something called proxy, and that proxy address actually has a benefit such that you don't necessarily need to do this type of YAML file, kind of modification. I will show you that shortly. And you can see this model. It also the ROM has kind of this type of convention where it just got this MLFlow artifacts, submit, and then dash the experiment ID. So in this way, you don't necessarily need to modify it manually. I will show you that with an example using the linear regression model, since it's faster. So if we define this will give me like my model is linear regression stuff, and then of course there's a pipeline, and then I have model OLS. I can cover like the sklearn pipeline stuff in a separate video, but here the output is like the model and the model name, and then we could just train our linear regression model. And before we train our linear regression model, I actually want to set this. So we set the tracking URL, and then let's if you set the tracking URL to like a local server address, and then you open a new experiment. Let's say this is my new experiment, and then once you do that, right? This actually what this does nicely is that it will put your artifact location start using the proxy by default. So if we do this, not quite sure what is happening. Oh, sorry. In order to kind of use this, you have to actually spin up the MLFlow, because only you spin up the MLFlow, then this kind of server will sort of make sense. So let's actually MLFlow and UI. Let's spin up a MLFlow here. So the procedure is you spin up on the Google Drive, and then you sort of just run this to create your new experiment. This will connect to it, and then it will start using like these artifacts. It's a proxy magical address, and then it gives you this experimental ID. And you will see that in this way, if we start training, it starts fitting our OLS, our linear regression model, and try to save that in that experiment. You will see this time actually the model got registered because we are kind of not file. You can if you don't want to register it, you can rewrite the file, but essentially you can see that this is our OLS and this is the performance. And after this has been run, I suppose it already kind of saved that specific thing into specific drawing into this MLFlow location, where we could just look at it on the local. So on our local side, right? Let's say on our local side, I think our MLFlow is still running, and we could just go back to the default, and we have this new experiment already there. You could DCI default. This is the model that we logged 1 minute ago, and if you click directly on this, it will automatically show you the model. There's no you don't need to actually modify the PICE, because it's like using this magical PICE. So in my opinion, as a summary, right, the best workflow is actually you spin up a ML UI here remotely, and then you set up your new experiment through this way, where you had a URL, and then you set up a new experiment, and verify that you are actually using proxy address, not absolute address like file system or HTTP. You're using these type of things. And then when you run this, and if you install the Google Drive app, desktop app, it will help you sort of sync between Google Drive and local version and the cloud version, and the online version. And then you could spin up another local MLFlow UI, and that local MLFlow UI will help you just looking at all the experiment that you have been logging in the cloud. So that's the trick that you make it work. And also another thing, if you don't want to register, you could just modify this portion of the code, right? You could just say I want to comment all these out, and then you could just do, no matter which tab you don't register the model, that means you later on you will explore and choose to register your model manually, as I showed in several minutes ago. For the models that is not being registered, maybe this is not this one. So for the models that is not being registered, we could just hit here and register the model if you want. So by default, I don't register model until I make sure I fix all the bugs, and I think it's a model that worth registering. That's all. Stay tuned.